We see from Newton's second law, that a net force causes acceleration on the body. When the body accelerates, its velocity will change. Since momentum is a function of velocity, therefore a change in velocity also corresponds to a change in momentum. With these, we can say that the net force acting on the body produces a change in momentum of a body. To derive an expression of the net force in terms of momentum, let us consider a soccer ball of mass m, that moves initially to the right at a velocity, v sub I. When the soccer player kicks the ball, exerting a horizontal external force, same as the direction of the ball accelerates, changing its velocity to v sub f, after a later time, delta t, while traveling at displacement, delta x. From Newton's second law, net force is mass times acceleration. And we knew that acceleration is equal to the rate of change of velocity, v sub f minus v sub I, divided by delta t. So we rewrite net force as mass multiplied by the change in velocity, divided by time interval. From here, we distribute mass m to v sub f and v sub I. Here, we see the expression m times v, which is an expression of momentum p. Therefore, net force is equal to final momentum p sub f, minus the initial momentum, p sub I, divided by the time interval, delta t. Lastly, the expression pf minus pi, is the change in momentum of the ball, delta p. From what we have already learned about net force explained by this formula, force is mass times acceleration, this equation brings us to a whole new word definition of net force. Now, we redefine net force as the time rate of change of momentum of the body. It means that, in order to change the momentum of the body, a net force must act on it. Here, we see that the net force acting on the soccer ball changes the ball's momentum. This equation explains that a gradual change in momentum requires small amount force, while a sudden change of momentum requires large amount of force. To explain this concept clearly, consider this scenario. Imagine we have two crates of equal masses and velocities. Therefore, they have equal amount of momentum. Now, let's say that there are two cats standing on the other side of the crates. Can you spot the difference, aside from the colors of the cat? Very good. As you can see, this orange cat is standing closer to the crate than this black cat. Now, imagine there are two men, brave enough to stop the crates, in order to save the cats from being crashed. Who do you think exerted larger amount of force? Obviously, this man should exert larger amount of force than the other man, who exerted only a small amount of force. Since the orange cat is closer to the crate, there is only a very limited time for this man to stop the crate before hitting the cat. In other words, this man needs to change the momentum of the crate, as fast as he can, and to do that, he need to exert large amount of force. On the other hand, since this black cat is standing farther from the crate, there is a sufficient time for this man to save the cat. This man can exert smaller amount of force, resulting to a gradual change in momentum. Whenever a net force is exerted on the body, it acts a particular time interval. The magnitude of the net force can vary with time. To explain this, imagine you throw a ball of mass m against a wall and bounces back due to the net force acting on it by the wall. The ball hits the wall with an initial velocity, v sub I. As the ball touches the wall at time 0, the magnitude of the force exerted by the wall, which started from 0, begin to increase, as the wall tries to stop the ball. As a consequence, the ball will be deformed until the wall exerts the maximum amount of force. At this point, the ball momentarily stopped and started to bounce. As the ball bounced, the magnitude of the net force started to decrease, until it drops to 0, and finally, the ball loses contact with the wall at later time t. It is clearly that the magnitude of net force varies with time. Now, we can visualize this concept by sketching a graph called the force time graph. The curved line shows the magnitude of the force relative to time. The force is increasing until it reaches the maximum value at half of the time of collision, then started to decrease until it reaches to zero, completing the time of collision. This curved line creates an area whose base is equal to the time of collision delta t. The area under the force time graph is called impulse, denoted by the letter I. Since the force varies with time, we can somehow estimate the average net force acting on the ball by transforming the area under the curve into a rectangle, whose height is equal to the average net force and its base is the time of collision, delta t. So the impulse is the product of the net force and the time, delta t, in which the net force acts on the body. The SI units of impulse of Newton second, for as long as the net force is in newtons, and time is in second. Remember, the direction of impulse is the same as the direction of net force acting on the object. In this section, we are now ready to find the relationship between momentum and impulse called the impulse-momentum theorem. We learned that the net force acting on the body is the time rate of change of its momentum, and is given by the expression delta p over delta t. We have also learned that the impulse of the net force is equal to the product of the net force, and the time during which it acts on the body. From here, if we replace the net force by delta p over delta t, so here we can cancel out delta t. Therefore, the impulse I is equal to the change of momentum of a body, delta p. This equation describes the impulse-momentum theorem. It states that the change in momentum of a body during a time interval is equal to the impulse of the net force that acts on the body. In terms of mass and velocities, impulse is also given by the equation, mass m, multiplied by the change in velocity, v sub f and v sub I. Take note also that, even though the impulse is a function of momentum, its unit remains Newton second, and not kilogram meter per second. Although they are seeming equivalent, Newton second is an exclusive unit for impulse, and kilogram meter per second is for momentum. Now let us answer this problem. Problem number 2. In a particular crash test, a car of mass 1,500 kg collides with a wall as shown in the figure below. The initial and final velocities of the car are negative 15.0 meters per second, and 2.60 meters per second, respectively. If the collisions last 0.150 second, find letter A, the impulse caused by the collision, and letter B, the average net force exerted on the car. Now let us establish the given information. The mass of the car is 1,500 kilograms. The initial velocity is negative 15 meters per second. So this is negative because, in the figure, the car is moving to the left just before hitting the wall. Right after hitting the wall, the car bounces back at a velocity of positive 2.6 meters per second. Do not forget to indicate the proper sign of the velocities, or else our solution will go wrong. The time of collision of the car with the wall is 0.150 seconds. What we are going to do is we solve for the impulse, I, for letter A. For letter B, the average net force exerted by the wall on the car. Now we're ready to solve. For letter A, impulse, since we have given mass and velocities, so we use the impulse-momentum theorem, impulse I, equals mass m, multiplied by the quantity, v sub f minus v sub I. Substituting the values, 1,500 kg times 2.6 meters per second minus negative of 15 meters per second. The impulse is equal to 26,400 Newton second, towards right. For letter B, the average net force. Since we have already solved the magnitude of impulse, so we will use the other formula of impulse, net force times the time interval or time of collision, delta t. From here, we solve for the net force. Net force is equal to impulse, divided by the time interval delta t. Substituting the values, 26,400 Newton second, divided by 0.15 second. So the average net force acting on the car by the wall is 176,000 newtons, towards right. Wow! That is tremendous amount of force. We expect large amount of force since the wall changes the momentum of the car at very small amount of time. So there is a sudden change of momentum, therefore a large amount of force is needed. Surely, the bumper and the front part of the car will be greatly damaged. Actually, this process is used by car manufacturers to determine the effectiveness of installed airbag in protecting the driver and front passenger from any collision. Now, let us consider a problem involving impulse momentum theorem in 2 dimensions. Problem number 3. A soccer ball has a mass of 0.40 kg. Initially, it is moving to the left at 20 meters per second, but then it is kicked and given a velocity at 45 degrees, upward to the right at 30 meters per second. Find letter A, the impulse of the net force, and letter B, the magnitude of average net force, assuming a collision time of 0.01 second. Now, let us analyze carefully the problem. Imagine this is the soccer ball of mass 0.4 kg. The initial velocity of the ball, v sub I, is 20 meters per second to the left. Then the soccer player kicks the ball. After it has been kicked, its velocity becomes 30 meters per second, 45 degrees upward to the right, or that is 45 degrees above positive x-axis. The collision time is 0.01 second. Required quantities are impulse, and the average net force acting on the ball. Now take a look on this. This problem requires 2-dimensional analysis, because right after the player kicked the ball, its velocity moves upward to the right. So before we solve the impulse, we need to solve first for the x and y components of the initial and final velocities. The x component of the initial velocity is equal to -20 meters per second. This is negative since the ball moves initially to the left, while the y component of the velocity, v sub iy, is 0. The x component of the final velocity is v sub f, cosine of 45 degrees, and that is 21.21 meters per second, while the y component v sub fy, is v sub f, sine of 45 degrees, and it is also equal to 21.21 meters per second. After this, we're ready to solve the x and y components of impulse, I sub x, and I sub y, by using impulse momentum theorem. I sub x is mass m, times the change in x components of the velocity, v sub fx minus, v sub ix. Substituting the values, 0.4 times the difference of 21.21 and -20. So the x component of the impulse is 16.48 Newton-second. Now for the y component, we will do the same process. I sub y is equal to m, times the quantity, v sub fy, minus v sub iy. Substituting the values, 0.4 times 21.21 minus 0. So the y component of the impulse is 8.484 Newton-second. After this, we're ready to solve for the magnitude of the impulse. We use Pythagorean theorem, I is equal to the square root of the sum of square of I sub x and I sub y. Substituting the values, the magnitude of impulse is 18.54 Newton-second. Then we solve its direction, theta sub x, using the inverse tangent of I sub y, divided by I sub x. Substituting known values, so the angle is 27.24 degrees, above positive x-axis. So this is above positive x, since the x and y components of impulse are both positives, so the impulse is acting on the first quadrant. Letter B, for the average net force. Now that we have solved the impulse I, we can easily solve for the average net force using the formula, I equals average net force times the collision time. From here, we solve for the force. Average force is impulse, divided by the time of collision. Substituting the values, 18.24 Newton-second divided by 0.01 second, will give an average force of 1824 Newton-second. The direction of this average force is the same as the direction of the impulse. Now let us further investigate our answer so that we have a better understanding on its concept. We see that right after kicking the ball is launched at an angle of 45 degrees. Why the player wanted it to be that way? Can you tell the reason? Anyone? Very good. If the player wants to achieve the longest range the ball could reach, we learned from Unit 1, the ball must be launched at an angle of 45 degrees. And to make it happen, the shoes he is wearing must exert an average force whose direction is not 45 degrees, rather it should be only 27.24 degrees above the ground. To easily provide this angle, soccer shoes should be well designed, so as you can see, there is a slight angle on the tip of the shoe. This angle allows the player to kick the ball at a proper angle, without overbending his foot.